So how many people have been downstairs and seen any of the public, how many public displays do you think there are downstairs? Have you noticed any public displays downstairs? Okay, so hands up, how many do you think there are? Right, one? Hands up for one. Hands up for two displays. Three? Aha, good. Now I can stop panicking. Four. There's actually some of, I counted 5 displays downstairs, but it's interesting that a lot of people have been around, and that public displays are the sort of thing that you don't kind of become fully aware of. This is work I've done in combination with Emily Coleman's and Paul Marshall at UCL. And public displays are an aspect of ambient displays on a lot of these very similar technologies, and they create a large number of interaction questions for interaction research, because they're not the kinds of things that you can actually traditionally use a lot of traditional methods with. By their very nature, a public display tends to be a very discretional kind of interface. You don't have to use it, and they are designed in this very pervasive way to be glanced at like a clock on the wall, and that creates a huge number of interaction problems. Our work is very much based on the very excellent work of people like Juan Costa and Borchers, and what they were interested in is whether or not people actually discover the information on these displays. And what they did was they actually went and stood next to a display, or very close to a display, and then looked at people looking at the display. And what they found was that people pay attention very infrequently to the displays. Displays eye height, they said, tend to be more effective than ones above eye height. The surrounding context, items near a display, tends to encourage people to look at it, and that video content tends to be more successful at generating people looking at the display. This was further developed by Muller et al., and they were kind of responding to this typical problem of people doing public displays research, which is you put a public display out and no one interacts with it for hours on end, and you're sitting there kind of waiting for someone to please come and interact with this display. And in fact, there was a paper earlier on this week that was kind of trying to solve that problem in a different way. And they suggested that in many ways, when people go out into the environment, into the real world, within an in-the-wild study, people basically are overloaded with information. And what they tend to do in that situation is become more selective. And they created this term that is derived from banner blindness, which is a term the web people use for not looking at a web banner. And they just create this term display blindness to say that we actually filter out the displays, and we don't bother to look at them because we assume they have advertising on them, which for people doing research into displays is terrible, because it means if you have important information, no one's going to look at it. But we wondered about this, and we wondered how people actually were able to know that a display was going to be there in advance. So we decided to use a new technique. We took a mobile eye tracker, and these are the kinds of glasses-based systems that record what you see and what your eye's doing, and they're normally used for kind of doing interactivity with mobile phones. And we decided to apply this to actually people moving through the environment. So let's have a quick look at what you get from that. So here you see the kind of typical result. The little orange dot is what the person's actually looking at. And as you can see, there's a huge amount of information to actually understand as you're moving through the environment. So as a technique, what you end up doing is going through frame by frame. And what we did was we started off by categorizing what people were looking at to give a kind of context for the display. Oh, hang on, going slowly, quickly again. Try doing that one. Okay. So our experiment basically was we put 22 people into a shopping centre in London, 10 male, 12 female, all right-handed. And so here you can see someone actually looking at a wall. So we'd categorise that as architecture, anything that were, basically was part of the physical structure. Here you can see someone looking in the distance above the above-head display. We've lost signal, so we think they're blinking. Now they're looking at the ceiling. Now the head's scanning. This is kind of quite often you get people looking around the head movements quite rapidly. And at the end of that scan, they ended up seeing a person in the distance. So again, another category was person. The head will now go up to, and now they've started scanning a column. So again, that becomes categorized into architecture. They've swung their head back. They're looking at the floor. And now they're going to swing over and they're going to look into a shop. Anything that was in a shop or a product in a shop we regarded as product. And finally, they're going to move over and they're going to go and hit that display dead center. So at that point, we're quite clear they're looking at the display. And what's quite interesting was a lot of these glances are very short. And you have a problem about whether or not they're actually looking at these objects. But if you notice in a second, they're going to, okay, there's someone reading the text of a shop. And then hopefully they're going to turn over and look. Go on. Get there. Yes, good. Now they're going to scan this side column here. And what's interesting is that the head movement and eye movement compensate for each other as they scan down the edge of a building. Now they've gone back to look at the display. And this is very typical of what's known as the kind of landing effect, where people kind of return. And here they are looking at some signage. Now, the task we'd given the people was to go out and if they'd won, they would get £100 worth of money and they would have to be given the thing they've chosen. So they're engaging in a very realistic task of actually shopping. Okay, here's the scanning movement. So we can be fairly sure that the head movement, the eye tracking process is actually going quite well. Now watch the big overhead display. And you can see how it's changing from black to white, and it's not attracting the eye in any way whatsoever. And we'll come back to that in a bit. So with these categories, we can then go back and actually measure in a program called Anvil how long they're looking at a particular thing for. And we end up with some very interesting results. So if you notice that this bottom column here, the green ones, this is how long a display was actually potentially visible for someone during their wayfinding process. So 26% of the time, a display was potentially visible, and it was visible for about 2.5 minutes. If we look at the distribution of time, the first thing that you notice is that people are spending about 40% of their time looking at products, and this is their task, so that's not very surprising. And it's in a shopping centre, so it's designed to be looked at. The thing I found really surprising is they're spending about 40% of their time looking at this incredibly dull, unremarkable building. Okay? And one hypothesis for that is that people are actually building up large, complex, three-dimensional models in their head to help them navigate through the shopping centre. They're looking at people 13% of their time on average. Now again, people are interesting, people are fascinating, and there are also kind of potential collision problems, so that's not particularly surprising. But the interesting one was people are spending about 5% looking at the names of shops, 1% looking at signage, and so therefore they're spending 3% looking at digital displays. Now that sounds like a small number, but remember with display blindness, our theory is that number is 0. So in fact, that's a huge increase. That's an infinite increase on 0. The other way we can test this is by, initially people emerged out of the space and they were, we started off from the same location, and they would actually see a number of displays typically, and they would, most of them would go one way or the other, and they'd cross a particular display. So we looked at the number of times someone looked at a display when they passed it, and it was in their field of view of one sort. So for this one, the one that you saw earlier, display A, this is technically called a MINF, by the way, a plinth, multimedia plinth. People were typically looking at that 44% of the time. 44% of people looked at that display as they emerged out of the system. The above-head display, people were looking at 60% of the time. So 60% looked at it. So, okay, those were the early numbers. They kind of decay a bit. But again, compared to 0, it's a very huge number. So display blindness. It doesn't exist. But why did they make that mistake? One thing to do is look at how long people were looking at the displays for. And the interesting thing was, for example, with architecture, people were spending half a second looking at architecture. And people were spending a third of a second looking at the displays. Now, if you imagine I'm standing here, or you're looking at me over here, and I'm looking over there suddenly, could you really tell if I'm looking at something for a third of a second? It's very difficult. The second thing was using, with due deference to Father Ted, things that are close up are bigger than things that are far away. And we can use that mathematically to actually work out how far the person was from the display when they first noticed it. If we plot that, we discover that, in fact, people are actually looking at displays of the first time they look at display from quite far away. That's sort of 5 meters plus. On average, it was about between 5 and 8 meters away. So again, if you're 8 meters away, it's very difficult for me to notice if you're actually looking at that display. So again, this is, there's a kind of iceberg problem going on here. We discovered some very interesting stuff. The first was the power of context. We did a thematic analysis of what people were looking at when they looked at a display. And we came up with a number of categories. We had scan and hit. So the head turns and it hits a display. There's not much you can do about that, apart from make sure you're in a location where people are looking around. Obviously, people are looking at the building quite a lot, so actually having your display near near something that people are looking at in architecture is actually quite useful. So here you can see the edge of this atrium, the eye's going along it, and it's hitting a display in the distance. Here, you can't really see in this version, but you've got a bright display against a temporarily dark background. And again, having a strong luminance change is a big help. Equally, if you have a dark display in a light background, that can also be quite helpful. People are also, I mean, this is an extension of the honeypot effect. If someone's just walking past a display, people look at people, and then they look at the thing next to them, which is a display. And here you see a better example. They're looking at that person, and then the display's behind them, and they look at the person. The other category actually was frequently there was looking back. People would look at a display for a very brief amount of time, look away, and then look back at the display. So if we look at the distribution of all this, we found that 24% of the time, people were looking at the building, and then they were looking at the display. So in fact, the context of your display is an powerful way of getting your display noticed or not noticed. Obviously, the display gets looked at in several times, which is, again, something that we have to think about. There are lots of systems that use eye tracking to notice people looking at displays. And in fact, what's actually going on is there's a kind of blinking behavior going on. Then you've got the bright display and the people. Let's just move on slightly. The other thing that we noticed was this effect, which I'll end with because it wasn't really part of our study initially, but it's kind of part of the potential future work. If you notice here, this video on the loop, you'll see that the display is flickering and the eye is not moving towards it at all. It's generally thought if you have a big kind of display going, whee, over here, then people will be sucked into looking at it. And I'll leave you with this video of people completely failing to notice animations and movies on displays. So there's one in that corner here. There's one here. Look at this bit. That's a display. And look how close the eye is. And then it moves. The eye does nothing. Oh, you think maybe it should be closer. Okay, so that's the big white display. It blinks. And even though the eye is next to it, it doesn't do it. The peripheral field of vision doesn't really seem to have a massive effect. Here, someone's preferring to look at the underside of an escalator than at these two very aggressively moving displays nearby. And here they've looked at a display and it flickers as they look away, and they still don't go back to it. So anyway, with that, I will open for questions.
Thanks a lot, Nicolas. We have time for a couple of questions, and well, okay, thanks.
Hi, Edward C., Smart Technologies. This is really interesting work. I'm wondering, given what we know about people looking at architecture, how can the displays be better situated such that you maybe hit those points where they're going to see, say, in the architecture, maybe that's where displays should be located. Can you give some insight into architecture and the location of displays?
Yeah, I think, and again, we don't have a huge amount of data for this, but I think what's going on is that people are quite often tracking lines of perspective. So in this room here, we have these very strong lines of perspective on the ceiling. And if your display is at the end of that line of perspective, then people are going to be tracking along, and then they're going to hit that display at the end of the line. So in many ways, I found this quite interesting because one of my kind of areas of interest is the impact of space and architecture on the interaction process. And I think it kind of backs up that as a kind of great reason for doing more research in the area.
Interesting work. Thank you.
Anthony Hornoff, University of Oregon. This is ambitious work and very difficult to do. I think it's really difficult also for you to come to the conclusions that you've come to here because of the tremendous error that's in eye tracking. And I didn't see any discussion in your paper of what you've done to embrace or to manage the error. The second to last video that you showed where you're saying, look, they're looking right over the display, right over the display. I suspect they were looking right at the display.
Certainly there's a certain amount of error in the display. I think one of the things that we were quite interested in was that when you're looking at people looking at the world, firstly, the eye tracking was done for about 15 minutes. So there wasn't a huge amount of time. I know there's been other work for much longer periods where clearly over a longer period you would get decalibration going on. We're working for those short periods, and what's interesting is that often you will see the head and eye compensating for each other as they kind of move down the edge of an object. And I think that kind of suggests to me that actually the calibration is still kind of okay at this stage.
Well, I would just encourage you to just try to embrace, to accept that there is error and try to embrace it.
Oh, there certainly is error, yeah. But again, you know, one of the problems with this as a methodology is it's incredibly time-consuming because you've got a human being doing it. If it was a machine doing it, which is what happens with most web-based stuff, yes, it would be completely off the wall.
Jörg Müller-Aarhus University, very interesting work, thanks. I think we have a little bit different understanding of display blindness. I always understood it as not any people ever looking at displays, but rather at people ignoring displays because they expect advertisements, and they expect advertisement. And in order to ignore something, you at least have to know that's there. So that might explain, like, people look at it very shortly. And the question that I have is, did you look at the ground distribution of architecture versus people, where the other things in the field of view in that situation, and how that differs from the distributions of views that you got in your data?
Could you say that again? The ground distribution of...
If you would just look randomly at the same image that you have where people are walking around, how would that differ from where people looked using your eye tracking data?
No, I'm still not really following the question.
There was a lot of architecture.
There's a lot of architecture, yeah.
And then there's a lot of people.
Yeah.
And people looked mostly at architecture, and the second thing that they looked at was people, right?
Yeah.
So I wonder if you compare the eye tracking data that you got to just the distribution of architecture versus people versus other things in that location.
I mean, certainly there was a variance in terms of the amount people, some people spent about 40% of their time looking at other people, and some people looked less. And we did it over different times of the day, and again, partly that was the busier times of the day, there were more people and less people. But in fact, it was very difficult to tell, the human variance was more important than the architectural or the kind of number of people around variance. What was interesting was I thought that when there'd be a lot of people would be looking at other people more rapidly. And I think what was interesting was that people looked at people in the distance. They tended to not to look at the people close up. So you don't tend to look at people walking towards you. You tend to not be looking at them. So you're not sort of inspecting people and kind of being rude. And again, there's the interesting process of the fact that people are using their peripheral vision when they're dealing with persons close up.
Quick question. What happens if I stick an e-paper display there? So something that's not backlit, is that a display? Because it's a confound, do we know what a display is?
Certainly, when I was doing the analysis, you kept looking at displays thinking, oh, is that a display or is that just a backlit piece of...
That's why I picked the opposite example.
Yeah.
Right? It's something that is a display, but...
I think it's interesting that
so
people...
Is the study about backlit objects?
It's effectively about backlit objects. Although there weren't really any... People weren't really significantly paying attention to backlit objects. I mean, there weren't that many.
Cool, thanks.
Okay. Yeah?
I want to welcome now to Bernd Huber from Technische-Universität from Germany, who's going to present detecting user intentions at public displays from foot positions.
This one. Yeah, I tried. Thank you very much. I'm going to talk about interactive information displays, and you probably have walked around this convention center and have watched there a variety of information displays where you can extract locational information, for example. But as we've seen in the previous talk, it's very difficult in public places to make users aware of such displays, and especially in interactive systems where we need the people to get to actually interact with the system. It's very difficult to use it, and the classic graphic user interface actually fails sometimes to show people that the system is interactive, and actually people might feel, for example, awkward to interact with